Hi, this is Roger from Kanka Labs, and today it's the second part of our series about our little UNIREL interface. In the first part I explained what you can do with it and demonstrated all the functionality in quite detail. And now it's about how the circuit works and what tricks our circuit designer Burkhard Kanka has used just to make all the functions available with just one CMOS IC and one transistor and just a handful of passive components. So there is a little bit to learn for you how to make use of as few components as possible to achieve some nice functionality. And I give you an advice because we use a power relay which can switch a mains voltage and mains current. There are always two things you should be aware of, and that is the ratings of the relay, especially the amps rating, because even if it can switch 8 amps in the case the relay that we are using, this is not true for a DC voltage, and this is not true when you switch reactive loads. We have two separate tutorials. One of them is already online, and depending on when you're watching this video, even the second one will hopefully be online from now on in about 1 or 2 months, where the difference between AC loads and DC loads and the difference between resistive loads like incandescent light bulbs or reactive loads like motors, transformers, etc., or switch mode power supplies. What's the difference and what you have to watch out for, and how the amps rating is derated when switching DC currents or DC loads and when switching reactive loads. So now let's start and take a look at the circuit diagram. Now let's take a look at the schematics, at the circuit diagram of our UNIREL, and see how all the functions are realized. For the first part we neglect all this circuitry here because we assume that jumper 1 is open, and we only take a look at the direct PC input. Now there's first of all, for protection, there's a current limiting resistor R8 with a value of 10 kilo ohms. Then we have a reverse protection diode D4. This serves the purpose that there can never be a negative voltage present here at the base of the switching transistor, which would immediately destroy it, but only positive voltages can get to the base, and only a positive voltage will do anything with the switching transistor. So after going through R8 and D4, there's still this voltage divider resistor R10 of the same value, 10 kilo ohms, and it has a double purpose. It also pulls the base of the transistor low when there's no signal present, because when we have an open jumper, then otherwise the transistor would be hanging in the air and would have no defined potential if there wouldn't be this pull down resistor. Now let's try to calculate what minimum voltage will switch the resistor on. First of all, we took the C version of the BC548, which has a current amplification of at least 200. Now the relay takes about 70 milliamps, and here this the LED with its current limiting resistor R11 have a negligible current compared to the current through the relay solenoid, and so 70 milliamps of relay current divided by a current amplification of 200 gives us a current of 0.35 milliamps base current necessary to switch the switching transistor on, which is of course also 350 microamps. Now let's keep this in our head, that the base current needs to be about 350 microamps to energize the relay and switch the signaling diode on. So we saw that we need 350 microamps base current at least, or at max, to switch the switching transistor on. Now this 350 microamps are also flowing through this diode, and they must flow through R8. Now the question is, what voltage do we need to have a current flowing of 350 microamps flowing through R8 so that we have enough base current? Well, about half a volt or 0.6 volt is lost here in the base emitter junction. Another half volt is lost here, and well, the voltage that must be above R8 is simply this 350 microamps times the value of the resistor according to Ohm's law, and this is 10K. So we multiply by 10 kilo ohms and we get 3.5 volts. So 3.5 volts are falling off here, half a volt over D4, half a volt over the base emitter junction, which translates to about 4.5 volts. We neglect the current here through R10 because there are only 0.5 or 0.6 volts here present through the action of the base emitter diode. And so 4.5 volt, or let's round it up to 5 volts, are 100% sufficient to switch the switching transistor on. And usually we use 6 or 12 volts for controlling the PC input. So when 5 volts are sufficient, then 6 or 12 volts of course will be sufficient as well. Now let's make back of the envelope calculation. What happens if we get a high voltage spike here on the PC line? Let's assume there would be 100 volts present, at least for a short time, here. Now the current through R8 will be 100 volts divided by 10K. This gives us 0.01 amps or 10 milliamps, and 10 milliamps is still safe for the base of the emitter, at least for short pulses, so that a voltage pulse of 100 volt will do no harm to our circuitry. Of course, if you put a low impedance source, voltage source of 100 volt for a longer duration on the PC input, then R8 will evaporate in the end, because the power that is generated with a 100 volt voltage over R8 is simply 100 squared divided by 10K, which gives 1 watt of power that is generated as heat here in R8, and this will finally destroy R8. But for short pulses, the whole circuitry is safe up to 100 volts present on not only on this input, but as you probably can see, also the other inputs are protected with series current resistant current limiting resistors. So that was the function of the PC direct control input. Now let's close the jumper and first of all take a look, well, what happens when the output of this flip-flop goes either too high or too low. Well, when it goes too high, it will also switch the transistor on, even if the PC input is low, because when it's low there can no current flow through to the base because of the reverse protection diode D4. So in the low state it will turn the transistor on in the same manner as a positive voltage here will do. And what happens if we have a high signal, a positive signal here, and now the input is low? Well, the current through R8 is still sufficient to keep the transistor in the on state, and a low here at the output cannot pull the base of the transistor low enough to avoid switching of a positive signal at PC. You can imagine it as if this resistor here is now in parallel, because when this is low it's connected to ground, and we have R9 and R10 in parallel, which gives us 5K to ground, and this will have nearly no effect on the current through R8 and the necessary base current to switch transistor T1 to the on state. So let's sum it up. The PC line can only with a high signal switch the transistor on, but it will always switch the transistor on, no matter, even if jumper 1 is closed and even if this flip-flop is, the output is in the low state. So we've mentioned a few times that the PC direct control input can only, with a positive signal being present here, do anything. It overrides whatever the output of the flip-flop will be, and will always switch transistor T1 on and will always engage the relay. But it cannot do the other way, and if you want to reverse that, well, there's a simple solution. If you want that a positive signal here always switches your load off, then just reverse the usage of the normally open and normally closed contacts, and in that case, when you have a positive signal, well, the transistor switches on, the relay is engaged, but now, because you have connected your load to the normally closed contacts, it will now change over to the off state. The normally closed contact will switch over to the off state, and that way you can realize the reverse function, namely that a positive signal definitely switches your load off instead of on. Simple trick, but then you have to remember also the function of set and reset are reversed, because when you use the normally closed contact, then everything is reversed, not only the action of the direct PC input. So finally I'll show you a trick how to connect more than, or how to switch more than 2 loads. You might remember that we have 2 completely separated contacts at the relay we use, with which we can switch two absolutely separated loads with a UNIREL. But what if you want to switch more than two loads on or off? Well, under special circumstances, you could just parallel them. Let's connect the center tap of the switchover, of one of the switchover contacts, to ground or to the negative supply voltage at whatever potential this may be. And now we have here the normally closed contact and here the normally open contact. And now we just parallel as many loads as you want. Of course, you should never do this with mains connected loads. That's absolutely a no-go. And you connect them on the upper side to their positive supply voltage. So, as long as the total current through all loads is below 8 amps for non-inductive loads, or accordingly lower with inductive loads, then this is a simple way of switching more than two loads. We even only need one of the contacts. On the other contact we can still switch one or more other also paralleled loads, but remember the limitation of the total current. And we could still do another trick, this time shown for the normally open contact. We even could, under special circumstances, have parallel loads which are connected to different supply voltage, which means the first one is connected to VCC1, the second is connected to VCC2, and the third one is connected to VCC3. There are two things to remember. They will switch to a common ground or a common lower supply voltage, and well, if even in the off state there can be current flowing this way, and you have to be sure what you do if this is possible with your application, but at least it's a possibility to switch loads in parallel with only one contact, which are even at different supply voltages. So this is something for the specialists, but a neat little trick to give one relay contact even more possibilities than only switching one load. So that shall be it for our little UNIREL, our nice little universal relay interface. I hope you liked it, and if yes, then give it a big thumbs up, or if you have questions you can do it down below in the questions or comments sections, or jump over to our forum. And hope to see you next time at another part of our video series. Bye from Roger, bye from Kainka Labs, thanks for watching.